Lab 3 Black Hole. The purpose of this lab is to use pre-existing position data in a GlowScript code of a star orbiting a black hole to find the mass of the black hole. One important assumption made in this lab is that the gravitational force by the black hole is the only force that the star experiences. The first fundamental principle in this lab is Newton's second law. Newton's second law states that the net force on an object is equal to its rate of change of momentum. Furthermore, the rate of change of momentum as well as the net force are split into parallel and perpendicular components. The parallel component is responsible for the change of speed of the object and is parallel to the direction of motion. The perpendicular component is responsible for the curvature of the motion and points towards the center of the kissing circle. It should also be noted that the parallel component of the net force is equal to the parallel component of the rate of change of momentum. The same can be said for the perpendicular component. These principles will be used to solve for the gravitational force on the star. Newton's universal law of gravitation is also used in this lab. With the net force, the mass of the star, and the distance between the black hole and the star known, the mass of the black hole can be calculated. To begin the code, initial conditions needed to be established. The mass of the star is given in the lab prompt. The time step is also given as 1 day. First, we are going to solve for the rate of change of momentum and set it equal to the net force by Newton's second law. The initial and final velocities of the star were already included. The initial and final momenta of the star were calculated using the initial and final velocities. The star's change in velocity and momentum were calculated. dp dt can then be estimated to equal the change in the star's momentum over the change in time. Lastly, given Newton's second law, we can set the net force equal to the rate of change of momentum. Next, we can calculate the parallel and perpendicular components of the net force. The unit vector of the momentum was calculated, as well as the magnitude of the rate of change of momentum. The parallel component of dp dt was then identified as the product of these two quantities. Then, by Newton's second law, the parallel component of the rate of change of momentum is equal to the parallel component of the net force. The perpendicular component of the rate of change of momentum can be obtained by understanding that dp dt is the sum of its parallel and perpendicular components. Again, by Newton's second law, the perpendicular component of the rate of change of momentum is set equal to the perpendicular component of the net force. Finally, the mass of the black hole can be determined. The magnitude of the net force was established, as well as the magnitude of the distance between the black hole and the star. Ultimately, Newton's universal law of gravitation was used to approximate the mass of the black hole. Here is the resulting computational model. The orange arrow represents the total net force. It represents only the gravitational force by the black hole and the star, therefore it always points towards the black hole. The pink arrow represents the perpendicular component of the net force. It is responsible for the curvature of the path and always points towards the center of the kissing circle. Lastly, the blue arrow represents the parallel component. It always points tangent to the kissing circle and parallel to the direction of the momentum vector. The mass of the black hole varied with each data point. In order to get a single approximation for the mass of the black hole, I used an Excel sheet to calculate the average of all of the data points. Here is the final calculated mass of the black hole. The what does it mean question asks to discuss the differences between the parallel and perpendicular components of the net force with those of the rate of change of momentum. By Newton's second law, there are no differences between these components. The parallel component of the net force is equal to the parallel component of the rate of change of momentum, and the perpendicular component of the net force is equal to the perpendicular component of the rate of change of momentum. The what if question asks if a different black hole were placed in the same location and the star experienced the same motion, could a different value be calculated for the new black hole? As you can see, the mass of the black hole only depends on the gravitational force on the star, the mass of the star, and the distance between the star and the black hole. Firstly, the mass of the star does not change. The gravitational force was calculated solely based on position data. Therefore, if the position data doesn't change, the gravitational force on the star will not change. Furthermore, the new black hole was placed in the same location. Therefore, the distance between the two bodies remain the same. Because all three of these values remain the same, it would be impossible to discover a different value for the mass of the black hole. The computational model would also remain identical.